Welcome. This lecture is on digital signatures. So digital signature will provide authenticity of the data. So the problem of deciding whether or not data that is presented to you originates from a particular entity. So let's review how this works. We have, in this case, Alice and Bob, and Alice wants to convince Bob that she issued a document. So Alice creates two keys. One is public and given to Bob, and the other one is private. And then with her private key, she's able to issue a signature and then sends the message and the signature to Bob. Now, Bob, by looking at both, by looking at the message, the signature, and using the public key, Bob must be able to convince himself that Alice was indeed the sender of the message. Now, note that a signature scheme provides authenticity but not confidentiality. So here, Bob has to be to authenticate a certain document. Bob has to be able to look at it. Now, what is the security game? So, unfortunately, in chosen messages attack, is a very standard notion of security for digital signatures. So how does a chosen message attack security game work? So we have a challenger and an adversary. The challenger, so the first of all, the challenger draws the key. So the private one stays with them, and the public key can be assumed to be known by the adversary. Now, the adversary wants to create a forgery. A forgery is a valid document, and a document and a valid signature for the verification key they have. Now, it's a chosen message attack because they can choose messages, send them to the challenger, and then the challenger must sign them with their signing key and send back the signatures. So the challenger receives signatures for chosen messages, and then after that, the adversary needs to come up with a new message that was not one from the signing queries that they submitted, together with a signature, such that the verification with the verification key is successful. And so we say that they win if they can win this game, and we say that the scheme is secure if there are no efficient adversaries succeeding in this game with non-negligible probability. So one of the most obvious things that we could try is to sign with the RSA function. Remember this function where f evaluates with the public exponent and g inverts f with the private exponents. Now, so the private exponents are e, and then such that it is co-prime with phi of n for n the public modulus, and the private exponent is the inverse of e. So we could use this as public and private key respectively. And then we could define the signing as raising the message to the power d. So this time it's sort of inverse from the encryption scenario where we first exponentiated with the public exponent. And that's because the first person to do something is the signer. So the signer will take the public exponent and then raise the message to the power d, and that is a tag. Now we could define that as the signature. And how would the verification work? Well, you just decide to accept if when you given the tag, you raise it to the power e, and then you fall back on the message modulo n. So as an example, if you have P and Q of 61 and 53, same numbers from our say encryption examples, and then we choose this exponent and there's its inverse here, and we pick the message to be 65. Now the tag would be the message to raise to the power d, which is here 1393. Now remembering that the raising it to the power e yields 1393, so to the 17 mod n, and that's 63. So if we see that as the verifier, we decide that the tag was valid, the signature was valid. Now, what is the problem here with this? So it has to do with, again, the malleability of the RSA function. So we can define a chosen message attack against the RSA function used to sign messages that will yield a success probability of 1. So assume our adversary picks 2 messages and asks for the signatures of those messages. So in this case, raising those messages to the power d. So the adversary receives those those tags, and then the adversary decides that M is the product of the M's, the MIs, and the tag is the product of the tags. And it turns out that the product of the tag is a tag valid for the product of the messages. And because of that, this pair message tag is always valid. And so the attacker succeeds with probability 1. So we need to do something in order to sign with the RSA function, but without, we have to mitigate the malleability. So the public and public key parameters are the same, except for the fact that we will use a hash function h, which maps to elements between 0 and -1. And then here we perform exactly as before, the same operation as before, except that we'll hash M and then raise it to the power D. And the verification is you verify by raising the tag to the power E and verifying that it equals the hash of the message. And if that's the case, you accept. So here we have, so we've seen how signing with RSA is possible, but also we can sign using El-Gamal. And in particular, so those El-Gamal signatures, for example, can be used in the context of signatures with elliptic curves. So these are very standard. So how does El-Gamal signature work? So assume that you have your favorite group, which in our case is usually z mod pz star, a hash function, an element of the group, and the public key is g to the x, okay? So h, and of course, the private key is the x in question, so the exponents that such that h equals g to the x. So to sign, you pick a number that is co-prime with the order of the group, in this case p-1. So once you have that, you calculate g to the h, and you calculate s, which is, so you have to hash m subtracted by xr, okay, which you know because you know x, and then multiply by the inverse of h modulo p-1, which exists because you chose h to be co-prime with p-1. And the pair rs is your signature. Now you accept it as the verifier if the following property holds true. So you take h, raise it to the r, multiply by r to the s, and then you verify that this is g to the to raise to the power h of m mod p. Okay, so that's seems like a pretty convoluted way to verify. It is correct because here is how we can rewrite h to the r times r to the s. So h to the r is g to the xr, and then s can be replaced by its function here. And then because everything that happens in the power is mod p-1, you can replace. So you can replace this. You can distribute your h, and then you will have that this will be equal to minus xr. Okay, so and so you split your terms here. So you have your g to the x, your h times h inverse. So that's the g to the hm. And then h times h inverse, and so the minus xr here. Okay, so these two will cancel each other, and you're left with just g to the hm. So the El-Gamal signature scheme is correct. So we in this very short video, we saw two examples of digital signatures, one with the RSA function and one using the discrete log problem. And we had a look at how to properly define the security of those schemes. Thank you very much for your attention.